Okay, so welcome everyone, and thank you for joining us today for this very special webinar jointly organized with our partners and your fellows of Solid Sense. Today we will dive into language subsetting and compiler qualification in the development of software for safety critical systems. As usual, this is Lavinia, and today's speakers are Roberto Bagnara, CTO of BUGSENG, who will cover language subsetting, and Marcel Beemster, CTO of Solid Sense, who will cover compiler qualification. So what a better team to give you a complete overview. On one side, we have BUGSENG, who has built the Eclair static analysis platform, which allows almost complete automation of the checks for MISRA compliance. And on the other side, we have Solid Sense, creator of the Supertest suite, which ensures verification of the correct operation of the compiler with respect to the applicable ISO standards. Just a quick note before we start, please write your questions in the Q&A section throughout the entire webinar, so at the end we can read them and reply straight away. All right, then let's turn this over to Roberto and Marcel.
Okay, so let's start. Here is the outline of the entire presentation. I will go through some important aspects of the C language, and then I will introduce MISRA C, and then I will let the microphone to Marcel for compiler qualification, and in the end we will see some synergy between language subsetting and compiler qualification, and then we will draw some conclusion. So, it's a usual disclaimer. I am a member of the MISRA C working group and of WG14, which is the ISO standardization group for the C programming language. However, the views that are expressed in this presentation are mine and of my co-authors, Marcel in this case, and not necessarily they do represent the views of either working group. So let me briefly present BUGSENG for those of you who don't know us. BUGSENG is a supplier of tools and services for software verification. We have been doing research in my research group at the University of Parma for more than 20 years. We have a particular focus on quality of the analysis and accuracy of the results. We have offices in Parma and in Pisa, and the Eclair software verification platform, which is our main product, and with the associated qualification kits, provide cost-effective support for satisfying several objectives of the major standard for functional safety, so ISO 26262 and the other that you see in the slide. The rhetorical question with which I start usually this kind of presentation is, what do you prefer? Do you want to reason in assembly code, which is what you see here, or do you prefer to reason about your code in C? So I guess the answer is you want to reason in C or even in C++. I'm talking more about C in this webinar, but everything I say applies equally to C and C++. So let us focus on the C language. There are very strong economical advantages of the C language, and they are summarized in this slide. So first of all, C compilers exist for almost any processor, and C compiler code can be very, very efficient without hidden costs, meaning that discounting the issues with multi-core processors, a competent programmer can guess more or less what is the computational cost of any piece of code. C allows writing compact code without too much verbosity. It is defined by an ISO standard, and in C it is quite easy to access the hardware, which is essentially in embedded programming and system programming. And C has a long history of usage included in critical systems, and C is widely supported by tools. However, the original spirit of C that WG14 keeps alive hasn't changed much, and it can be summarized into this commandments like trust the programmer, let the programmer do anything, and speed is more important than portability, and so on. And as you know, many of these things are bad for safety and security. So what is the problem? What is the issue? The issue is rooted into the notion of behavior, which the C standard documents define as something that is visible to the external of the program. So external appearance or action. And due to this, all compilers observe what is called the as-if rule, meaning that the compiler can do any transformation provided the observable behavior doesn't change. This is not a peculiarity of C only. It's also true in C++ and other languages. It is true in all languages that have been designed to admit an optimized compilation implementation. So in this, having to preserve only the behavior observable from the external world lie many of the opportunities for optimizations in the compiler. So there are several kinds of behavior which are quite dangerous in C if one doesn't know them. So the most dangerous one is undefined behavior. It's when you use some non-portable or erroneous program, or you use it on erroneous data. And in this case, when the standard says it is undefined behavior, or when the standard says nothing, then it means that the standard imposes no requirement, meaning absolutely no requirement. The program may crash. It can exhibit erratic behavior of any kind. It can even format your hard disk. Okay? What normally this means is that the compiler assumes undefined behavior does not happen. If it does happen, it is a fault of the programmer. The programmer has violated the contract constituted by the ISO standard, and so warranty is void. Anything can happen. Let's start with a simple example. It is undefined behavior when the program attempts to modify a string literal. So here we have an example program where there is a string literal, hello, with 3 exclamation marks, and the smart programmer decided that 3 exclamation mark is too much. So the programmer wants to get rid of the last 2, so it sticks a null termination character in position 6 of the string. However, this is undefined behavior because the string, the literal, can be allocated in read-only memory, and so trying to write to read-only memory can result into another exception that from the language level can literally have any effect. Another variety of non-completely defined behavior is unspecified behavior. This is when there are 2 or more possibilities of doing one thing, and the standard doesn't impose requirements on which possibility is chosen in any instance. So let me show this by means of an example. So one of the unspecified behaviors is whether in an addition, and here we have a sum operator, this plus here, whether the left-hand operand is evaluated before or after the right-hand operand. So in this case, you see that the functions hello and word print hello and word followed by an exclamation mark in this case. So since it is unspecified which one is executed first, this program might print hello word, which is probably what was intended by the programmer, or it might print a word exclamation mark hello, which is probably not what was intended. So it is important to understand that when it is unspecified behavior, the compiler needs not to document the choice and needs not to be consistent. So for example, if you change the optimization level, the choice might be different. You can get a different output, or you activate debugging and the choice might be different. If I complicate the example and instead of returning immediately, I complicate main by computing this sum 10 times, there is no obligation whatsoever on the part of the compiler to compile every occurrence in the same way. The compiler can call hello first in the first instance, and it can call word in the second instance, and so on. The other kind of implementation-defined behavior is similar. However, the difference is that this must be documented. So implementation-defined behavior, again, is when there are two or more choices of doing one thing, and the compiler has to fix this choice and document it. And what happens is that many compilers provide different implementations for implementation-defined behavior. We will have a seminar less than 1 week from now, where I promise you that I will surprise you. I will definitely surprise everybody on the consequences of implementation-defined behavior. Most people know implementation-defined behavior. Everybody in this audience knows that there are implementation of C for 16-bit machines, where int is 16-bit, implementations for 32-bit machine where int is 32 bits. So the sizes of the primitive data types are implementation defined. There are many other implementation defined behavior. There are more than 100 in all versions of the language. So we have described undefined behavior, unspecified behavior, implementation defined behavior, and we didn't talk about locale specific behavior because it's not so important for this presentation. So the natural question is, why is the standardizer language not fully defined? Why there are so many degrees of freedom, and why there are such dangerous things like undefined behavior and unspecified behavior? And the reason is that because in this way, implementing compiler is easier, and most importantly, implementing efficient compilers that generate faster code is easier. Let me go deeper in undefined behavior. We have said that attempting to modify string literal is undefined behavior. So let's suppose that we have a program where there are literals. One is tail, and the other is head-tail. Well, the compiled program, in order to save memory, can store only the second one, can store only head-tail, and return a pointer to the fifth character as tail. So given this permission that, thanks to this undefined behavior, the compiler has, changing one string, if you succeed, may also change the other in a way that can completely surprise the programmer. So we have two possibilities. If the literal is in read-only memory, you get another exception. If you don't get another exception because the literal are in read-write memory, then you believe you have modified one, whereas in fact you may have modified many of them. Another interesting example is this one. So the behavior is undefined when an expression is shifted by a negative number or by an amount greater than or equal to the width of the promoted expression. So this is the example. So it is quite easy to understand why shifting by a negative number is forbidden by the standard. So it's the spirit of C is not the one of inserting extra code. So if the shift count could be negative, the compiler would have to insert instruction to check the sign of the shift count. If the shift count is negative, then it would have to do something. For example, I don't know, if the language was defined saying that shifting a quantity -2 positions to the left is the same as shifting it by 2 positions to the right, the compiler should generate code to make the test, negate the value, and then do the opposite direction shift. So no, it is a bit less intuitive to understand what might be the problem shifting a 32-bit integer 32 positions to the left. Because one might reason, well, if I push 32 more zeros from the right, the result should be 0. And the answer is no. Because on very popular architectures, such as Intel 64 and Intel Architecture 32, the first thing that happens to the shift count is that it is masked. So only the 5 low-order bits are retained. And this is done in the machine code in order to facilitate providing an upper bound to execution time of shift instruction. So on this machine, shifting by 32 position is the same as shifting by 32 position masked, retaining only the 5 low-order bits. However, this mask gives 0, so it's the same as shifting by 0 position, which is the same as doing nothing. So you see, under our interpretation in this slide, the result would have been 0, whereas in this architecture, the result is unchanged. So for speed and ease of implementation, C leaves this behavior undefined. So the philosophy of C is that whenever this is possible, an high-level construct is mapped to one machine instructions. And given the variability there is in machine instructions for the different architecture, this explains a lot of undefined behaviors. Okay, now let's go to MISRA C. There is a relation between this and MISRA C. Let me first introduce MISRA C. It's a project that started in the 1990, initially funded by the UK government, and now it's completely self-supported. So the original MISRA publications were this one, the first one on the left, the development guidelines for vehicle-based software, were the first automotive publication concerning functional safety in the automotive sector. And it is truly remarkable because it was published more than 10 years before the work started on ISO 26262. In April 1998, we had the publication of the guidelines for the use of the C language in vehicle-based software, so the first version of MISRA C. This picture resumes the history of MISRA C. At the beginning, we had the Ford and Rover, and they were using their internal coding standards for the C programming language. And in the framework of the MISRA project, they joined forces to produce MISRA C in 1998, the first edition, which influenced pretty much every coding standard for the C and C++ programming language that was published afterwards. And the latest version is MISRA C 2012, and now I will explain you something about MISRA C 2012. So first, let me make clear what is the relationship between MISRA C and language subsetting. So, and what is language subsetting? The point to be understood is that the weakness of the C language comes from its strength. They are a package. So the good point comes with the corresponding bad point. For example, the facility with which you can write efficient compilers for almost any architecture is one, as we have seen, one of the main reasons behind the non-definite behavior. The fact that you can write efficient code without hidden costs is because there is no runtime error checking. So if you want to do extra check, for example, if you want to make sure that your index doesn't go outside the bounds of a certain array, you, the programmer, write the code to make the check. So the fact that there are many compilers and the language is defined by an ISO standard, which is a very pragmatic body, it means that it's another reason behind non-definite behavior. So if two well-established compilers do the same thing in different ways, then we will have to compromise. So the behavior will not be completely defined. Hopefully, it will be implementation defined, and in some case, we have to make it undefined. But This is the other main reasons behind non-definite behavior. The fact that it is easy to access the hardware is the same reason why it is so easy to corrupt the program state, for example, by overwriting the stack. And the fact that you can write compact code, it's a reason, the same reason that makes it possible for context like the C obfuscated context exists. So it is possible to write completely ununderstandable code in C. So what is the solution? The solution found in industry was language subsetting. So you don't program your critical applications in C, you program them in a subset of C where the possibility of running into bad things is highly reduced, and in some cases it is completely removed. So language subsetting is now mandated or recommended by all safety and security related industrial standards. And today, the most authoritative language subset for the C programming language is MISRA C. So that's why we are interested. So what is MISRA C 2012? It's a document, okay? It's around 200 pages where a collection of guidelines are presented. So every guideline is introduced by a pink strip like this one. There is on the left a unique identifier, which is composed by a classification, which is either rule or directive. We'll see the difference in a minute. And then a unique, and then a number that together with this classification constitutes a unique identifier. And to the left of this unique identifier, there is what is called a sentence, a short sentence, which is called the headline of the guideline. So the guidelines, as we said, are either directives or rule. They are directives when the information concerning compliance is not completely contained in the source code. In order to decide whether the code complies or not, you usually have to take into account requirements, specification, design, or even the programmer intention. Whereas when the information about compliance is only contained in the source code and in the implementation defined aspects of the implementation, then it is called a rule. A rule can be machine checked if it is decidable. We have no time now to delve into the difference between decidable and undecidable rule. However, just take into account that directive means only machine checkable if you provide further information, and rule in principle is machine checkable. There are then three attributes, a category for a guideline, which can be mandatory, required, or advisory. The analysis attribute is a pair. The first item is either decidable or undecidable, and the latter one is either system or single translation unit. And then there is the attribute applies to, which is a set of language versions separated by comma to which the guideline applies. So when the category is mandatory, you can only claim MISRA compliance if you obey the rule. So no deviation is permitted for mandatory guidelines. Whereas when the category is required, you can either comply or justify why you are not complying. So the justification must include an assessment of the risk involved in not complying, and it should contain a plausible argument, defendable in front of a peer, that will have to be convinced that indeed there are no risks involved. Advisory guidelines are just recommendations. They should be followed as far as reasonably practical. You need not to raise formal deviation if you do not observe them, but non-compliances should be documented. So they should be listed at the end of the project. So I want to just show you a very small selection of MISRA rules. So the first one is very important, and it connects to compiler qualification very well. So Rule 1.1 of MISRA C 2012 says that the program shall contain no violation of the standard C syntax and constraints, and shall not exceed the implementation translation limit. So the code must be written in the chosen version of C, and it should obey the syntax and the constraints, and moreover, the translation limit should not be exceeded. So why is this important? It's important for two reasons. So one is that language features that are outside the supported version of C have not been considered when developing the MISRA guidelines. So warranty void if you use them without any assessment of the impact. And you should know that a conforming implementation does not need to generate a diagnostic when a translation limit is exceeded. And an executable may also generate it that doesn't work as expected. What is a translation limit? Every compiler has limits, okay? For example, the number of, the maximum length of a source line is a translation limit. The significant part of external identifiers is a translation limit. The maximum depth to which you can nest conditional compilation directive of the preprocessor. Okay, these are translation limits. For example, for C90, a compiler can be legitimately called a C compiler if it implements a maximum depth of conditional compilation directive of 9, if I remember correctly. It means that if you go deeper, 10, you do not even have the guarantee that the compiler will give you a diagnostic. So, and the generated output can do just anything. And it is full of implementation, it's full of compiler that even fail to diagnose constant violations. So as Marcel will say, one of the important parts of supertest is to check whether these compilers provide the diagnostics that they are meant to provide you. So rule 3.2, I chosen this because it has to do with comments. So it's a typical thing that people would say, what's the problem with comment? Okay, well, there are problems with comments. For example, this rule prevents the line splicing used in double-slash comments. The point is that line splicing, meaning putting a backslash at the end of one physical source line, is a way to construct a logical source line by joining physical source lines. And this can harm you. So here is an example. The programmer wrote a comment, a double-slash comment, and the double-slash comment contained at the end a path of a Windows folder. Okay. However, following the Windows syntax, the line of the comment ends with a backslash. So this is line splicing. This means that critical function, which we presume was critical to be called, will not be called because the function call will become part of the comment. So the subsequent stages of the compilation will not even see the call of critical function. And of course, we will not get any warning. And the critical function was, say, compiled out without the user even knowing. Another example is rule 13.2. The value of an expression and its persistent side effect shall be the same under all permitted evaluation orders. This has to do with unspecified behavior. We have seen this at the beginning of the presentation. The point is that between two sequence points, the evaluation order is unspecified. So if you don't know what the sequence point is, think about the semicolon as a sequence point. There are other sequence points, and not all semicolons are sequence points, but this is a good enough approximation. The point is that the compiler can compile code, has to compile code in such a way that it is as if all what is to the left-hand side of the sequence point has completed execution before execution of the part of code that is to the right-hand side of the sequence point begins. So in addition, there are situations in which not just the evaluation order is unspecified, you can even have undefined behavior, such as when you try to modify an object more than once between two sequence points. So let us see an example, which is the best possible thing. Here we have two volatile variables, and volatile variables are used to model, for example, memory mapped register in the hardware, and reading a volatile variable can cause an effect, a behavior which is visible on the outside. So since it is unspecified, the order in which the arguments of a function call are evaluated, in this example code, we have a violation of the rule, because we don't know, looking at the code, whether the side effect of TCNT1 is executed before or after the one of TCNT2. So the proper way to comply to this guideline is to use temporary variable, so that here you see we have sequence point. These semicolons are sequence point. And so this way we have forced the order of execution of the side effects connected to the reading of the two volatile variables in the way we wanted. We want first the side effect associated to TCNT1, then the other. Okay? Okay, so over to Marcel for compiler qualification now.
Thank you, Roberto. Let me see if I can set this up.
Okay, in the meantime, shall we launch a little poll before Marcel parts?
Yes.
Okay, so have you ever been hit by a compiler bug?
So the answer are never, or only once, more than once, or several times, in such a way that compiler bugs really are a nuisance for your work.
Okay, so 5% never.
Lucky guy.
Yeah, really. 76% more than once, and well, the results are slightly changing now, but 15% several times, and anyway too often for my taste. Okay, Marcel, up to you.
Okay, thank you. That's quite interesting, those results. Yeah, I'll come back to that. So I'm going to talk a little bit more about the compiler qualification. So Roberto already explained that the compiler has quite a lot of responsibility in implementing the program correctly. And yeah, my name is Marcel Beemster. I'm from Solid Sense in the Netherlands, and well, our main goal is to have this test suite. We have this test suite that is used for compiler and library checking for C and C++ compilers. So we validate that the library and the compiler implementation indeed are compliant to the language specification. That's basically the one thing we focus on. And yeah, we provide a product, so you can do this testing yourself, but we can also provide services. Now, let's talk a little bit about the impact of compiler errors. If you're working on a safety critical application, such as maybe the controller for the brakes in your car, then it's obvious that you want this software to work perfectly, and you will put a lot of work into verifying that the source code of your application is correct and that the application works well. But there's also a huge responsibility on the compiler to do the correct compilation of that program. Every single line in that program goes through the compiler and it ends up in your car, in the car, and maybe possibly millions of cars. So there's a responsibility for the compiler as well. And generally, compilers are seen as trustworthy. But as we've just seen in the poll, I don't know if those results are visible, but as we may have seen in the poll, only 10% of you have never hit a compiler error. So yes, compilers are very good, and compilers can be trusted in many cases. But apparently 90% of the viewers here, the audience here, has actually run into more than one compiler errors. And one of the difficult things of those errors is, well, one, it may not show up easily. It may happen only in one particular case. And the other thing is, when it does happen, it's very awkward to debug those things, because basically you're trusting the compiler to do the right thing. Now, that trust, is that proper? Can you really trust the compiler? I've done a test run with the GCC compiler. The precise version is not so relevant. This will happen also with the latest version of GCC. And what we see here at the top part is verifying for compile time errors, and that includes checking the diagnostic of the compiler. And that's an area where many compilers are quite weak. And in this case, we also see that the default settings of compiling C++14 with GCC, we get quite a number of failures in the diagnostic, about 200 in total. You can reduce it with the right option settings, but for GCC, you can't get it down to 0. We've also got a couple of runtime errors, far fewer, and that's a good thing, of course. But GCC is a very, very widely used compiler. And if you're working with compilers in embedded systems, those compilers are not so well tested as this GCC compiler for an x86 host. So here are a couple of errors. These are not errors in GCC, by the way. These are some of the errors that we run into in our career as compiler testers. So here we see a small piece of program where we assign 42 to an entry in an array, and then we have an alias to that array. We have a pointer to the array, and we assign -1 in the same location. So we actually override the value of 42 here using an alias. Now the compiler can make some assumptions around about arrays and aliases, but what should never happen is that in this place the compiler will assume that the value of S0 has not changed because there was an assignment through a pointer with an alias. Maybe it doesn't understand about aliases, but at least it should never assume that the value has not changed. Now, in this compiler that I was using with this test, this was an embedded compiler for embedded systems. The compiler assumed there was no change, and then it ran into the wrong code there because it assumed that the value was still 42. That's really bad. Here's another example. It shows something that is relevant for how you use the compiler. This is using, I think it was, it might have been GCC, it may also have been LLVM, it doesn't matter what compiler, using Linux subsystem for Windows. So that allows you to run Linux programs on a Windows system and execute Linux programs. And in this case, I used a Linux compiler, an LLVM or GCC compiler, and I executed this piece of code, compiled and executed this piece of code. So I have a long double variable. I initialize it with a value of 1.3, and then in the assertion, I add a small positive value to 1.3. And well, normally you would expect, of course, that the resulting value is at least equal, but probably larger than the original value of LDVAR. And this assertion fails in this particular setup because the Linux compiler, the LLVM compiler, has a different idea about floating point precision than the Windows system. And the compiler is okay because the compiler was built for Linux and it was built for an 80-bit long double system. Windows is okay because Windows is built for 64 bits, but the combination of the two, it fails. And that means that, basically I would not trust any floating point heavy code on a Linux subsystem for Windows. This is another error. This is in the Intel ICC compiler. The Intel ICC compiler has quite good standing in the x86 community because it is quite good at and aggressive at optimization, and it beats out GCC in many cases. But it also sometimes makes errors. And in this case, this is a reasonably simple loop. I have done something very tricky here because I start counting at the minimum integer value. So that's the special case of this piece of code. If you do that and the compiler compiles this with optimization, so it means it will try to vectorize the code as well, and it will simply run into a segmentation fault at runtime because the compiler assumes that it can compute with values that are slightly below I. And in this case, there's nothing below I because I started at the minimum integer value here. So that's another, an error in an actual compiler that you can run into. Okay, I'm going to talk a little bit about safety of the compiler because we're talking about compiling programs for safety critical applications. And the world of safety, or functional safety as it is called, started out, well, more than 150 years ago when the Industrial Revolution caused explosions in places that were not intended. There were explosions before, those were usually part of war, so that was intended, but steam engines started to explode where people were around, and that was not a good thing. And people got concerned about the safety of these industrial machines. So that is where the field of functional safety started. It is now a very well-developed field with lots of branches into all kinds of the industry and consumer goods, and they help keep our lives safe because we are surrounded by things that can be potentially harmful to us. Now, there are even functional safety rules for compilers, and they're part of, they're called tools in the case of compilers. And the goal is to develop confidence in the use of your compiler. So you can be confident that the compiler you use does indeed produce the right code, and that code should abide to the behavior of the program as was intended. And we do that for a specific use case. So you make that, you develop that confidence for the way that you use the compiler. There are many different ways to configure the compiler, but you're interested in the way that you use it in particular. You do that by verification of the language specification of the compiler against the language specification. So you check that the compiler generated code conforms to what is defined in the language standard. Now, not all compilers will pass this verification. In fact, we have never run into a compiler that passes all of these verification. And so you have to define mitigations. You have to define workarounds where the compiler does not abide to the required rules. Now, this is formalized in one functional safety rule, ISO 26262 for the automotive industry, in the chapter about tool qualification, other functional safety standards for the industry in general, which is applied to robotics, for example, for the rail industry. They have their own functional safety standards, and they usually also have a section for tool qualification. The nice thing about ISO 26262 is that it describes a very nice process. It really guides you through the compiler qualification, and that's a very useful thing because, if you're interested in building an application using the compiler, then that safety process, in principle, it looks like overhead, so you want to make that as easy as possible, and that's where ISO 26262 really helps you. It's also important to note that the qualification responsibility, the development of this confidence in the tool, it's a responsibility for the user of the compiler. You cannot leave that to the vendor of the compiler. You cannot say to the vendor, give me a compiler that I can trust. And the reason is that the vendor will not have tested that compiler for the specific use case that you are using it. compiler qualification may seem like a pretty daunting task. Compilers are extremely complex, so where do you start? Well, there, ISO 262, as I explained, it can help you. It can help you make these steps, and by doing the steps one at a time, you can get through this. So these are the 5 main steps that are defined in ISO 26262. And the process is basically, first you have to plan how you're using the compiler. That is part of the documentation of the qualification process. Evaluation of, do I have to qualify the compiler? How do I qualify the compiler? So that's the next step. Then you have a choice of different qualification methods, although for compilers there's only one choice. That's reasonable. And then step 4 is actually the big amount of work where you do the validation, the testing of the compiler, and you also define these workarounds, the mitigating actions for the problems that you have found. And finally, you have to nicely document this. And yeah, depending on what confidence level and the ASIL level, you may have to instigate an external review as well. So step 1, the planning of the usage of the compiler. So you have to define the maximum ASIL levels. You have to also identify what kind of measures are already in place to detect malfunctions of the compiler. It is not by default the case that if you have good application testing in place, that it is sufficient for compiler testing as well. So we have a nice a white paper on the side. I think you'll get a link later about optimization testing, and that really shows that if you don't really test specifically for certain actions and optimizations of the compiler, this is not something you will find by simply application testing. You need to define the language specification, of course, against which you want to be compliant. You have to plan also, you have to write down which compiler am I using, where's the user manual, what are the known failures that the supplier has provided. And the final thing is that you really define the use case. So how is that compiler used? What are the options that you're using with the compiler? What environment are you using it on? What target are you executing the code? Those things. Step 2 is tool evaluation. The main goal of this sort of stepwise process is to find out, do you need to qualify or do you not need to qualify? So for example, if the impact of an error in the compiler is not big, then you don't have to qualify the compiler. So if you're not compiling for the brakes in the car, but you're compiling for something far simpler in the car, maybe a dashboard light, something simple, that is not that an error there may not have a very high impact. In that case, that would mean that you can step out of this scheme here and simply say, okay, I don't have to qualify my compiler, I'm done. The same is true for the tool error detection level, although I already said you have to be very cautious, and the standard also says you have to be cautious with saying, okay, I have my application testing in place, so I will find all the compiler errors. That's not necessarily the case. So in general, you will end up here in the last step, and that's where you can have a choice of 4 qualification methods. Now that also depends which choice, depends a little bit on the ASIL level, but actually for tools, for compilers, there's not that much of a difference what kind of ASIL level you're aiming at. So these are the 4 qualification methods. Confidence from use is one, but compilers there are regularly updated. For GCC and for LLVM, you get 3 updates per year if you want to use the latest version, which also includes bug fixes for previous versions. So that may be an incentive to use that. Yeah, there is not increased confidence from use because the compiler is really not that old. And every new version of compiler, yeah, you should really treat it as a different compiler. Evaluation of the tool development process, very complicated because it needs insight in the development process. So what did the supplier do to build that compiler? In the case of open source compilers, there may be thousands of people literally who have worked on the compiler. So there's not a tool development process that you can simply evaluate. And the 4th choice here is that the compiler itself was developed according to a safety standard. As far as I know, that simply does not exist. There's no compiler that has been developed according to a safety standard. So that leaves validation of the tool, and that means testing. Now, testing is not perfect in the sense that it will guarantee you to find everything. But if you have a good test suite, such as our Supertest test suites, then that will give you a good understanding of any errors in the compiler. So what we do with Supertest is validate the compiler against the language specification. So by running the tests, we gather evidence that the compiler is compliant to the language specification. That's the basic thing that we're trying to do. We provide with Supertest also the link between the tests and the language specification. So that's part of the requirement traceability that's built into the V model, which is often used in functional safety qualification procedures, not just ISO 262, but others as well. Step 4 is then the validation of the tool itself by testing. We test for compliance with the functional specification for that specific use case that you're using. So if you're using a particular optimization flag, that is the one that we're testing. A very big part, and that's already what I already said, a weak part of compiler compliance is also correct recognition of errors in the compiler, giving the compiler the correct compiler diagnostics. And that's often a weak point. There's also the case that the compiler is not required to diagnose any undefined behavior because, as Roberto explained, the compiler can assume, it is allowed to assume there is no undefined behavior in the program because that makes it, allows it for better optimization, generate faster code. So it doesn't have to generate diagnostics for undefined behavior, and we can also not test that. So that's a weak area. So this is where static checkers come in, like Eclair from BUGSENG, and also where you want to define a language subset, such as the MISRA subset, to avoid these cases that are hard to get compiler diagnostics for. Now there are also just diagnostics that should be given by the compiler and that are not given by the compiler, and for those you have to define mitigations. And one of those mitigations can again be employing a static analysis tool, because those static analysis tools are often more critical about the code than the compiler itself is. So the final step is writing all this down and then maybe have a confirmation review by an independent third party. And that basically completes the qualification process. So it's not rocket science. You can step through this one by one. And if you have a good test suite, then that can really help. So Supertest is such a test suite. Fundamentally, it's just a very big bag of handwritten tests. Our handwritten test collection is huge. I think for C++14, it's around 20,000 tests or so, test files, and each test files can contain many more tests. I've written here these X's as well, so those are the tests for the diagnostics of the compiler. So those are supposed to fail, supposed not to be compiled, because the compiler has to give an error in that case. And then we have even bigger collections of generated tests for particular implementation-defined arithmetic behavior, for example. Also the calling conventions. So I'm not going to go in detail here about all the features that we have here. You can find that on our website as well. One thing I want to highlight is that we do also support bare metal targets. So if you want to run on a small board here, even if it has very small instruction memory and very small data memory, we can run Supertest on that board, and that makes it possible to have confidence in your compiler, even for a very tiny controller. There are many of those tiny controllers. I recently talked to a developer who was working on the controller for the dials on the dashboard of the car. So the speed dial, for itself has a little processor, and that's connected to the bus, the general bus in the car. that is what controls the dial. Now that processor is really tiny. There are also processors in the car that control the windows going up and down. That's one of those very small, tiny processors. So yeah, what we've learned and what you've learned as well, because 90% of you did run into compiler errors. No compiler basically is perfect, and in mission critical, in particular safety critical applications, you do want to know about the weak points of your compiler. So testing the compiler, it can be done both by compiler developers, and I would recommend compiler developers to do that, but also by compiler users, because that's a requirement of the functional safety procedures. So one final optimization error, and I'm presenting this now because I'm going to give this one to Roberto, because this was an error that we found not so long ago in GCC. And okay, I'm not asking you to understand C++ here, but this is a class that inherits from another class, so there's an inheritance structure, and here we have some casting going on from a pointer to a B object here to a void pointer, and then here we cast that void pointer back to a pointer to A or a pointer to B. Now this is all legal. You may, in terms of the language definition, you may say, well, I would never write this code. This is ugly. This is not never happens in reality. But if this would happen in reality, then this particular compiler, the GCC compiler, failed this test, because for one of these tests over here, it decided that the value was false instead of true, and that fails the test, and that was an optimization error. It happened only at higher optimization levels of GCC. So with that example, I want to switch back to Roberto. Thank you for your attention, and well, if you have questions, please submit them, and we can come back to them later in the webinar. Roberto, please.
Okay, thank you, Marcel. So I am restarting sharing the screen. I hope it works. Let me check. Yes, it works. I'm sharing the screen. Okay, so synergy between language subsetting and compiler qualification. So as Marcel explained, qualification suites test the standardized features. So the specification to be tested, the requirements are given by the ISO standard. So, and they do not test extension. It would be too difficult to test the extensions provided by different compilers with different philosophies and so on. So, and this is one of the important reasons why MISRA C and C++ add specific guidelines for enforcing standard syntax and constraints, enforcing translation limit, and limiting the use of extensions. So compiler qualification enables the use of C++. I mean, you have no justification at all to use C or C++ with a completely broken compiler. So everybody does this, even if they do not engage in formal compiler qualification, because they do not work in safety critical system or critical system anyway. They must have some trust in the C compiler. Okay, and language subsetting ensures compiler qualification is relevant. So if I remain in the limits imposed by the applicable ISO standard, it means that my compiler qualification exercise is relevant. So that's one important aspect of the synergy between language subsetting via MISRA C, C++, and compiler qualification. There is another aspect of the synergy, which Marcel hinted at. So since all compilers have defect, when you find them, the point is that you need to know whether your project is affected or not. And since you will always find bugs in compilers, okay, you can hope that the bugs are limited to a feature that you don't use. For example, complex number. It would be too good to be true. So and the point is that once you have found limitations as a compiler, you have to make sure that your project is not affected, or you have to know in which ways it is affected in order to apply countermeasures. And the static analyzer, like Eclair, can be used for this purpose. So, for an example, I will use the bug introduced by Marcel that has to do with conversion of void pointers to pointers to certain class types. And it is important to understand that its presence or absence in GNU version of the compiler does not follow a trivial pattern. So 7.4 is broken, 7.5 appears to be fixed, 8.1, 2, and 3 are broken, and it seems to be fixed in all version starting from 9.1. But what about the numerous GCC derivatives? There are, I don't know, dozens of compilers that are derivatives of GCC. So people takes the GCC development repository, they clone it at some stages, they apply several patches of their own, they make changes. So are these GCC derivatives affected or not? So this is very important to know, and it's not easy to find out without using a test suite like Supertest. So once you have found that the compiler you are using is subject to this defect, the question is your project subject to this defect? So what we did was to develop a specialized checker running on top of the Eclair software verification platform to detect the conditions upon which this bug triggers. So, and we ran it on several open source projects, and we found one, for example, I'm showing this project is a C++ project, LYX. I'm not exactly sure what it is. I think it is an editor. And here is the report generated by Eclair on this project. So the project is of respectable size. There are more than 2,200 source files, 400 translation units. So it's not really a small project, and there are 6 instances that are flagged by this specialized checker we have developed. So let me increase the size here. You see, so the checker was called GCC bug 89698, and there are 6 occurrences in the code that have been found by the checker. So here we have we have static casts from void pointer to a class type that is inheriting from another class. 6 instances, all in one source file. So this is crucial information for anyone that wanted to make sure that appropriate countermeasures have been used to make sure that the project is not affected. So it's time to conclude. There are concrete advantages of MISRA compliance and compiler qualification besides checking the box. So I know someone treats this important subject as box checking exercise, but this is wrong. So it's not just a matter of checking a box, because doing this will reduce time to market, because thanks to MISRA compliance, you will obtain with the final product with less reworking and retesting, you will go more quickly to the final product. And with compiler qualification, you can decouple application development from compiler testing. You will not be delayed by compiler bugs you know only at the end. So you know in advance about the bugs that may affect you in your project, and you will sleep better, because it is an important thing, because if you develop safety related software, you know that your company is liable. So in this seminar, we have shown that MISRA compliance and compiler qualification are synergic. So compiler qualification with software test is not rocket science, and Solid Sense provides services that can make it really easy for you to the point of qualifying for you your compiler. And MISRA compliance with Eclair is efficient and cost effective, and we also have services that can make your life much easier even if you use Eclair. Okay, so if you have questions, Marcel and myself will be happy to answer them.
Okay, thank you very much. The first question is about the unspecified behavior hello world example that you showed at the beginning. And the question is, by using always the same compiler version with the same flags, will assure to have always the same behavior?
Well, you will have to not only use the same compiler and the same version and the same flags, but the entire project should be identical. So you should be compiling exactly the same code in the same way, in the same environment. And then I think the pragmatic answer would be yes, you can trust that the result will be the same, but not by the letter of the standard. So by the letter of the standard, you don't have this guarantee. So I've given an answer that is not rooted into the C standard. It is rooted in my knowledge of tool chains and their environment.
Okay. Is there a new edition of MISRA C foreseen somewhere in the nearest future? It seems to be already 8-ish years without any update clarification.
Oh, well, no, this is a misunderstanding. So many things happened in these 8 years. So, for example, in 2016, Amendment 1 was published with 14 new guidelines to address security-related aspects of the C programming language. In 2017, Technical Corrigendum 1 was published with some important corrections, and then in 2020, we published MISRA C 2012 Revision 1, which is a rollout edition incorporating all the previous amendment and technical corrigenda. And the last thing that happened this year, in April, MISRA C 2012 Amendment 2 was published that extends the use of MISRA C to C11 and C18.
Which replies to the next question, which is C11 and C18 covered by the MISRA C 2012?
Oh, yes. So you can download MISRA C 2012 Amendment 2 from the MISRA website. If you don't find it readily, drop us an email. We will send it to you.
Okay, is it recommended to switch off the compiler optimization to be on the safer side for an ISO 26262 project?
I guess that's a question for me. I would say it depends. It depends if you can afford that, because if you're working on an embedded target, and that is really something that's going to be produced maybe in the millions of times, then there may be hardware limitations there in the size of the memory or the speed of the processor or the power that it takes that really require you to optimize the code. Because otherwise it runs out of the resource budget that you may have for that piece of code. And that's especially the case if you're talking about very computation heavy code that can be vectorized, for example. Even small ARM processors these days have vector units, for example, and if the compiler can use those, that's a great benefit for the research users. Now, if you can afford it, then actually I would say probably yes, because compiler optimizations are extremely complicated, and I would guess that more than half of the compiler source code is dedicated to compiler optimization. So there's a huge chunk of code that you would turn off in case you don't use optimizations. So yeah, of course, just to mention Supertest again, we do have a part of our validation suite that is directed to optimization. So we do have good tests for optimizations, and we really tried to do good coverage of all kinds of different optimizations in different circumstances. But even that, it's still testing. It's not a guarantee that all the optimizations are correct. So if you can afford it and it doesn't matter the speed and the size of your application, then for safety critical applications, I think I would personally choose to turn off my optimizations.
Okay, thank you, Marcel. Back to Roberto. This is a question on a class static analysis tool. Is it possible to specify parallel execution threads, for example, interrupt services routine for the tool and detect race conditions?
This is a service that is under design, and it will be released in later revisions of Eclair. So yes, it can be done, and it's not yet commercialized yet.
Thank you. Okay, back to Marcel. How much time does it take to qualify a compiler?
Oh, yeah, that depends so much on different things. One of the things that it matters for is what kind of execution engine are you using during the testing itself. So if you're testing on a small target board, that is usually quite a bit slower than if you're testing on a simulator, for example. So that has a huge influence on the time. We have many tests. So if you want to run 20,000 tests, and that's just a handwritten test, and it takes half a minute for each test, that's a long time before even the testing is finished. There's also potentially a lot of work in defining the mitigation. So if the compiler is found to have deficiencies, yeah, you have to write those down, you have to analyze those, and you have to provide mitigations for those. And those mitigations, they also have to be usable, of course. So they basically become part of the safety manual of the compiler that is given to the compiler developers, the application developers. And those application developers have to be able to work with those mitigations. So there may, in some cases, you may have a trade-off. What kind of mitigation do you specify? Is it over-specified, or can you be very precise? And then, of course, it's very, very nice if that mitigation could be automated, and then you can automatically check that your source code may contain potentially unsafe code. So, yeah, those are considerations. In general, I would say a fast compiler qualification process for the first time could take something like 2 weeks. If it's much slower, then I would say it could take maybe 2-3 months even. The nice thing is that if you have to requalify the same compiler, maybe for a slightly different use case or for an updated version, then things can go a lot faster. You still have to run the test, of course, but all the analysis and the documentation, that can be borrowed from the previous qualification run, and so you save a lot of time on that side.
Thank you, Marcel. Last question. How much would it cost to develop an Eclair-based mitigation checker?
Okay, so the short answer is that I don't know. So it's a new service, a service we are designing together between BUGSENG and SolidSense. It very much depends on the peculiarities of the bugs. So first we have to identify the conditions triggering the bug. This may require an interaction between BUGSENG and SolidSense, and then to develop a checker depends on the complexity of the checker. To give you an idea, the checker I've showed you was developed in a matter of a couple of hours, and the time that was mainly spent there was due to testing. But of course, testing these mitigation checkers can be tested in parallel, so many at a time, and so the testing time can be easily factored out. So I would say that it is something that is in the range of I don't know, for a condition that is rather simple as the one I've shown, it could be measured in a few thousands of euros, and also bundling together several mitigation checkers can reduce the cost significantly.
Okay, thank you, Roberto, and a special thanks to Marcel and to all of you for being here with us today. Of course, if more questions come to mind, you can always drop us an email at info@bugseng.com. Same if you want to have a chat about your projects, or more specifically, if you need to comply with MISRA, the BUGSENG team will be more than happy to guide you through it and provide you with highly specialized training and consulting services, and even with a free trial of Eclair. If you want to know more about C and C++ compiler and library validation, qualification, or qualification services, you can contact SolidSense through their website or with an email to info@solidsense.nl. To refer back to this webinar and share it with your colleagues, the recording will be available on BUGSENG's YouTube channel very soon, so make sure that you subscribe and turn on the notification bell to be the first to know when it's up. Hold on just a second. Next webinar is a super requested one, so mark the date. Understanding Implementation Defined Behavior in C and C++ will be on September 22nd, usual time. So if you haven't already, head over to bugseng.com/webinars and register. And that was it from us today. We look forward to hearing from you very, very soon and seeing you all next time. Have a nice day, everybody. Bye-bye.
Bye-bye. Bye-bye, everybody.
Thank you.
Thank you, Marcel. Bye.
Thank you, Lavinia. Bye-bye.